if you accept that you can choose a basis consisting of only eigenvectors or generalized eigenvectors for a vector space, I mean, so some operator is given to you, some operator A, let's say, and acting on some n-dimensional space, then if you accept that you can choose a basis for this n-dimensional vector space, which consists of generalized eigenfunctions of operator A, then you see you don't have to go through all that proofs. Because then it immediately becomes, I mean, then you can prove immediately that the Hermitian matrices will be, I mean, you can diagonalize Hermitian matrices. Because you can explicitly construct the matrix which will diagonalize the Hermitian matrix, right? I think towards the end I mentioned to you, right? So I don't know what, I mean, do you have any question? And maybe if you ask some question, it will be easier from the last. I should say some of the things I skipped actually in this chapter. I don't know. Yeah, okay, but so do you have any question from the, let's say, the Cayley-Hamilton theorem and the projectors that we constructed, the phi I A, right? The construction of those subspaces SIs, no? And you write S as a direct sum of all the SIs, and the SIs were consisted of generalized eigenvectors, right, with a particular eigenvalue lambda I. So that was the logic, right, of this proof. You have any question? So I mean, let me just remind you the steps. Maybe then you can try to ask. So the first step was to write the characteristic polynomial. Characteristic polynomial associated with the matrix A. So A is given. A is an n by n matrix, right? And then what we defined, this characteristic polynomial was simply the determinant of lambda times the identity matrix, this is n cross n, minus A. Right? So this is all n cross n matrix. Lambda is a complex number, arbitrary complex number. So this defines to you, this is a definition of this. This is a polynomial. So this is an nth degree polynomial. Nth degree polynomial in lambda. It's simply because it's an n by n determinant, so it's going to, the highest power is going to be lambda to the n. I mean, this will start as lambda to the n plus some lower coefficient phi n minus 1 lambda to the n minus. These are numbers, some constant numbers. These are constants. They depend, of course, on the matrix A, but with some number. Given a matrix A, this will be some number, all the way up to phi 0 times 1. Okay, so this is the characteristic polynomial. Then the Cayley-Hamilton theorem proves that, so what is the statement here? That phi of A is identically equal to 0. Where, so what is phi of A? You just take this polynomial, and wherever you find lambda replaced by, I mean, this you can think of it as lambda to the power of 0, right? After all, 1 is the same as lambda to the 0. But wherever you see lambda, you replace lambda by A. So this becomes A to the n minus 1, and this is lambda to the 0. A to the 0 is 1. We just choose a convention. So this will be, so this is the same as, we are saying A to the n plus phi n minus 1, A to the n minus 1 plus all the way up to phi 0 times the identity matrix. And the statement is that this is 0. That's what the theorem is. Yeah.
Why we need the Cauchy-Hamilton theorem? Because by the definition of the characteristic, if you put in place of lambda A, then that becomes 0, right?
No, that is not. I mean, this is not because. I mean, see here, what is happening is that, yeah. I mean, it naively looks like that, right? But that is not. I mean, that is not correct because. I mean, here when I'm computing determinant, I'm thinking of lambda as a number, right? and what is appearing here is identity matrix, right? The compute determinant. But now at this stage, when I have a polynomial, there, okay, I can ask the question, what happens if I just replace by a, right? So I mean, yeah, naively it looks like, yeah, if you just replace this by a, it looks like it's 0, right? But yeah, that is, yeah. Okay, so this is one thing. Then the next step was we constructed this phi a's, phi a, and you remember this construction, the way it proceeded was you first of all take the phi, 1 over phi lambda, and since, okay, this has n roots, right? This polynomial has n roots because it's the nth degree polynomial. I told you that I will prove it in the second chapter, this statement, but for the moment just assume that given any nth degree polynomial, and I want to I want to see when this becomes 0. Okay, there are n solutions of that, n possible values. Some of them may appear more than once. I mean, there can be multiplicities. So this in general will be lambda minus lambda I to the power of Ri product I, going from 1 to some k, where of course the condition is k, I mean Ri, I going from 1 to k is n, right? That's the total number of roots, which is okay. So then what we did, we took this phi lambda, and using this form of the phi lambda, I can always write it as sum fi lambda divided by lambda minus lambda I to the power of Ri, I going from 1 to k, where fi lambda is a polynomial of at most degree r minus 1, Ri minus 1. This is just what we call usually writing. I mean, you have 1 divided by that. You can always write it as a sum of the partial fractions, you know, that you can do. Okay. So once you do that, then if you can multiply this both sides by phi lambda. So let me multiply both sides by phi lambda. Then this is still true, right? But left hand side is 1. Okay. So what we are saying is that this whole thing, this I call phi lambda. This whole thing is I call phi lambda. Okay. Phi lambda. No, not this whole thing. So let's look at it again. So substitute this here. So what it is sum I equal to 1 to k fi lambda. And you see, when you multiply this, what's going to happen? I mean, this is a product of all of this, right? Let me put here j, okay, just to distinguish between this I and j. So you are multiplying this whole thing to that. So what is going to happen? This denominator will cancel exactly the ith term here, right? So what will be left over is all the remaining j's, j not equal to I, right? Because j equal to I term will exactly cancel with that, right? So this becomes product j equal to 1 to k, but j not equal to I. So you have to omit the ith term, lambda minus lambda j to the power of rj. Okay. This is what the form is. And then we call this whole thing as phi, gave a name to it. It's some polynomial. We just called it phi I. So this we called phi I of lambda. So therefore this becomes I equal to 1 to k phi I lambda. So this was identity, right? So it was just a complicated way of writing 1. But nevertheless, so what was the use of that? The point was that this phi I, so again, now what is this? Let's see the degree of this polynomial. First of all, you see this is here only thing which has been omitted is the j equal to I term, right? If I had not omitted, then this would have been exactly the phi lambda, which is degree n, right? But since I have omitted the ith term, you are reducing the degree by Ri, right? So this is Rj here. Since I am omitting the ith term, I am reducing the degree by Ri, right? So this quantity has a degree n minus Ri, right? But this one we said has a degree at most Ri minus 1, this fi lambda. So this whole thing has a degree at most n minus 1, right? So each of these objects I mean, this is Ri minus 1, and that is n minus Ri. So add them up, it becomes n minus 1. So this has degree n minus 1 at most. Degree. Okay. Then once again, you define the phi a by just replacing wherever you see in this polynomial lambda, you will replace lambda by a. Okay. So that's going to give me again some matrix, n by n matrix, because A are all n by n matrices, right? So this will be some n by n matrix, and what this identity is saying is that the sum of phi A is equal to identity matrix. This is n by n identity matrix. I equal to 1 to k. So this is a very, again, a nice identity, and so what is the most important point of this is that they satisfy the several properties here, phi I a times phi j a. So these both are n by n matrices, so just multiply the two n by n matrices, and then you find that this is equal to 0 if I is not equal to j, 0 as a matrix, n by n matrix. So 0 matrix is something which has all entries 0, right? And it's equal to phi a when I is equal to j. Right? So that was the next step. I mean, I'm just reminding you the steps last time, right? And that also shows you what is the logic of this whole proof. Okay, so this was the main thing here. So in a sense, phi i's are like a projection operator, okay? In a sense, because for the projection operator, we had two conditions: p square is equal to 1, p square equal to p, and p was Hermitian. Here we are not talking about there is no Hermitian. The notion of Hermitian is not there at this stage. But nevertheless, it satisfies the equation phi I square is phi I. So it's like a projection operator. Okay. Then we define the subspaces Si. These are the subspaces Si, which was the set of all the vectors which can be written as lambda, phi a acting on any vector V, where V belongs to the full vector space S, right? So this was the definition of Si. Then it's clear, because of this equation, that S can be written as a sum, direct sum, S1 plus S2 plus Sn, Sk. I goes from 1 to k, right? Because for every vector V, I can always use this identity. This is equal to identity, so I can rewrite this as sum I equal to 1 to k phi I a V. I just use this identity here, that 1 is equal to that. So, and then the individual term phi v belongs to Si. So any vector I can decompose in terms of a vector, some part which is here, some part which is here, and so on and so forth. I can write it as a linear combination of vectors from this. Okay, so this was one thing. Then finally, we showed that the Si, the vectors in Si consists of generalized eigenvectors Okay, that is, they satisfy this equation. So what was it? A minus lambda I times. So this ith space comes with the eigenvalue lambda I to the power of Ri, acting on any vector of this, let's say, let me just call it Vi equal to 0, where Vi belongs to Si. Okay. So that this implies that, this is true for any vector Vi of Si. So that means that every vector of Si satisfies this equation, right? And therefore, they are some generalized eigenvectors of rank less than or equal to Ri. Okay. So this is essentially, this basically proves to you that for any vector space, I can choose a basis which consists of only generalized eigenvectors. So idea is you choose some basis here, and these are all finite dimensional spaces because total dimension is n. So the sum of these dimensions must be n. So they're all finite dimensions. You can choose a basis here, choose a basis here, and so on. Okay. Also, one more thing is we showed that the vectors from here are linearly independent of each other. Right? You remember that was another statement. It is not only this. We also showed that if you take so the vectors from different SIs are linearly independent. Okay. Which means that if you choose, if you find some, if you look at some equation of the form Ci phi a acting on some vectors, I don't know, let's call it, let me say wi's. This need not belong to Si. These are arbitrary vectors of S. I going from 1 to k, and if you try to solve this equation that this is equal to 0, then you find that the necessary condition is, I mean, then it's necessarily all the Ci's must be 0. Therefore, these are linearly independent. This was the, so that was the proof of this statement that vectors from different SIs were linearly independent of each other. So as a result, then, if I choose a basis here and a basis here and a basis here, etc., then putting them all together, that will form a basis for the full S. Right? So this is the main step. So you know, that way, all this long detour was to prove that final statement. Okay, that you can choose that, and in that basis, the matrix A, comes into, can be put in the what they call canonical Jordan form. Okay, there's a particular form where there are diagonals. Diagonals are these lambda i's, right? And then there is only the one block of diagonal, one below the diagonal, with the entries 1, 1, 1 for the generalized eigenvectors. Now, if you apply this especially to the Hermitian operators, since we know that all the generalized eigenvectors are actually ordinary eigenvectors, right? They are all of rank 1. Okay, so that means since this is a general statement that you can choose generalized eigenvectors as a basis, combine that with the fact that for the Hermitian operators they are all of rank 1. That means that I can choose a basis for this vector space which consists of ordinary eigenvectors of a Hermitian operator, right? And once you have chosen that basis, then we explicitly constructed the unitary matrix which takes H to the diagonal form, right? So that is the idea. Yeah. Okay. Now, do you? You have any questions on the details of these proofs, or? Here today I didn't give the proof. I just told you the steps, right? For each of them, one has to, of course, prove statements. But perhaps you could try one thing. Yes, sorry, go ahead. How to get there? When I is not equal to j, right? Yeah, that was so this statement. Yeah, this was a very important step in the rest of the entire thing, to proving this statement. Right? It was a crucial step. So this is simply because of the fact that if you remember, phi lambda was of the form fi lambda times the product. Let's say k. Sorry, okay. Let me put here L equal to 1 to k, but L not equal to I. Lambda, what was it? Lambda minus lambda k, lambda L to the power of RL, right? That was the form of that was the phi lambda. So now if I take phi lambda with phi j lambda, A. So now the phi A will just simply become that, right? Where just you replace all the lambdas by A. So if you take phi of A with phi j of A and multiply this matrix multiplication, so this will become you have fi A times fj A. remember that, I mean, normally in the matrix multiplication, I cannot just commute, right? However, all this, the only matrix which enters is A and identity. So, right, I mean, so here is identity. The only two matrices which appear are A and identity. A, of course, commutes with itself, and also it commutes with identity, right? So therefore, for this computation, it doesn't matter. The ordering doesn't matter. You can move them as you wish. Okay, so there is that. And then I have a product here, L equal to L, let me just write, the range is clear, it's always 1 to k, L not equal to I here, A minus lambda L, identity to the power of RL, and let's choose something else, say M not equal to J, where again you have A minus lambda M times identity to the power of Rm, right? This Fj times this thing was phi j, right? Because here you are taking the product, but removing the jth term here, right? That was the, just put them together, and now use the fact that, I mean, for I not equal to j, what will happen? You see here, only the jth term is missing, right? Everything else is there. But if I is not equal to j, there will be a term with L equal to j here, right? I mean, suppose I is 1 and j is 2. Just take a simple example. Then here what we are saying is that everything appears except 1. So 2, 3, all the way up to k it enters. Here, everything is there except the 2. So you have 1, 3, 4, everything is there. So what is missing here? The m equal to 2 term is missing. But there is a 2 here. So I can put that together to complete it. But then that becomes phi a itself, right? And phi a we already, from Cayley-Hamilton theorem, we already know phi a is exactly 0, identically 0, right? So that's the way you prove. And the second one you prove by using the fact, so this is, this proves, so this becomes, I mean, this basically saying that if I is not equal to j, you can extract a phi a out somewhere, and then there will be something else here. But whatever that doesn't matter. The important point is phi a is already 0. So this is 0. Now if I equal to j, you can write it like this. Phi a, after all, is equal to phi a times sum j equal to 1 to k phi j a. Because we have the identity, this is equal to unit matrix, right? So I'm doing nothing, I'm just multiplying by unit matrix, so it's the same as that. And now when you multiply the phi I with the phi j, you see whenever j is not equal to I, it is 0 because you've already proven that. So the only term here which will survive is j equal to I, right? In that case, you just simply get phi I a square, right? So this way we say phi I a square is equal to phi I a. That was the statement, right? Any other questions? Yeah. Sorry?
Give me a vector, is there a method to find the ranking generally between vectors?
No, I mean that given a vector, no, that is, so you want to find out, given a vector, okay, given an eigenvector, a generalized eigenvector, what is the rank? Huh? No, is that given a matrix? I mean, you see, it's not so easy. I mean, okay, we can do it for 2 by 2 matrix explicitly. But in general, if you give me even a 3 by 3 matrix, if I have to do that on the blackboard, it will take 1 hour. You know, it's difficult. No, you cannot. You have to solve the problem. I mean, you have to really, write down the characteristic equation and find the roots. Which you know that beyond the cubic equation, you don't even have analytic expressions in general, right? So you have to be lucky to be able to explicitly work out. Okay, you can put it in the computer, maybe do numerically calculation and so on. That is a possibility, right? I mean, I would advise you to just, all this looks very abstract, right? But you could try the following. Just take some 2 by 2 matrix, because 2 by 2, I mean, everything is easy. It's just a quadratic equation, you know, with some numbers. You can just pick whatever numbers you want. Huh? And then for the matrix A. And then go through this entire thing. First construct the phi lambda, the characteristic polynomial, then then substitute lambda equal to A, and check explicitly whether this is 0 or not, you know, because it looks amazing, almost miraculous that, you know, this phi A should be 0. But you can try that for the 2 by 2 matrix, some simple 2 by 2 matrix. Actually, even this, I mean, why don't you try that? Because this will have a rank 2 vector. Okay, you can try this too. Okay, and then construct the. So actually, you can see. Okay, let me just do it. Actually, this is a sufficiently easy. I mean, even the quadratic equation is very simple, right? In this case, so I can just work it out. So let's take as an example that. But again, this is probably too simple. Let me make one more. Put here 2. Okay, 3 by 3 matrix. This is still sufficiently simple. I mean, although it's a 3 by 3 matrix. So let's compute lambda times identity minus A. Well, that is simply, this matrix is simply lambda minus 1, minus 1, 0, 0, lambda minus 1, 0, 0, 0, lambda minus 2. Right? Now, the phi lambda is simply determinant of this matrix. So phi lambda is, as you can see, this determinant is simply the product of diagonals. Right? You can open it from here, then it's clear. So it's simply lambda minus 1 square times lambda minus 2. So we have, so let's say we have only 2. Lambda 1 is 1 and lambda 2 is 2, with the R1 equal to 2 and R2 equal to 1. Right? That's those R1 and R2 are the powers here. Right? Indeed, you can see R1 plus R2 is 3, as it should be, because it's a 3 by 3 matrix and it's 3. Okay, so let's open it up. Let's open this up. So what we get here, so from here you get lambda square minus 2 lambda plus 1. And here you get lambda minus 2. So let's open this up. So lambda cube, lambda square term is what? Minus 2 and minus 2. So minus 4 lambda square. The linear term is plus 1 and plus 4. So plus 5 lambda and minus 2. Right? Okay. So now let's check if phi of A is 0. So A was this. So we substitute. So let's see. So we need to find out what is A square and A cube, right? Because there is you'll get A cube also. So let's see. A square is you take the square of that. So first term is 1. I mean this with that. This with that is 2, right? Is it 1? Yeah, 2. Huh? And this with this is 0. And this with that is 0. This with that is 1. And this with that is 0. And then finally this is 4, right? That's A square. And what is A cube? A cube is, I just multiply this with that. So you get here 1. And the second one gives you 3. Third one gives you 0. Here it is 0, 1, 0. And then 0, 0, 8, right? So now let's see if this is true. So lambda cube, so this matrix minus, so what is this? So this equation is 1, 3, 1, 3, 0, 0, 1, 0, 0, 0, 8. That's the lambda cube. And then minus 4 times lambda square. So I multiply 4 with that, minus 4. So plus, let's say, minus 4, minus 8, 0, 0, 0, 0, minus 16. Okay. Then plus 5 lambda, so plus 5 times A. So plus 5, 5, 0, 0, 5, 0, 0, 0, 10. And then minus 2 times identity. So minus, plus, let's say, minus 2, minus 2, minus 2, 0, 0, 0. Right? So let's see if it adds, if I've not made a mistake. Let's see. So look at the first term here. This is 1 minus 4 plus 5 minus 2, which is 0. Then you have 3 minus 8, which is minus 5, plus 5, which is 0. So you can check. I mean, let's see. The third one is, of course, every time 0. This is 0, that's 0. Here, 1 minus 4 plus 5 minus 2 is again 0. And finally, here, 8 minus 16 plus 10 minus 2 is 0. So indeed, it's 0. I mean, you see that explicitly. This was guaranteed from the theorem, Cayley-Hamilton theorem, but this is just to check. Now let's construct the phi I lambda. So what I need is, I need to write this as a partial fraction, sum of partial fraction, first of all, right? So 1 over lambda minus 1 square. So I want to write this as this times some, I don't know, alpha lambda plus beta plus gamma over lambda minus 2, right? And then just work it out. So this becomes, so this whole thing is alpha lambda plus beta times lambda minus 2 plus gamma times lambda minus 1 square, which is same as lambda square minus 2 lambda plus 1, right? When I take the common factor here, LCM. Now this should be equal to 1 because we are computing 1 over phi lambda, right? I mean, we are writing 1 over phi lambda as that. This is phi lambda already, so this better be equal to 1. So that tells me from here lambda square is coefficient is alpha, that is gamma. So therefore alpha is equal to minus gamma. That's one equation already because lambda square should disappear. Then the linear term is minus 2 alpha from here, and from there is plus beta, and then from here is minus 2 gamma. That should be equal to 0, but use the fact that alpha is minus gamma, so these two cancel anyway. So that tells me beta is 0. And finally, the constant term, here beta is 0 anyway, so that disappears, and here simply gamma. Gamma should be equal to 1, right? So therefore, gamma is 1 and alpha is minus 1. So the equation is simply this, minus lambda, and this is 1. I mean, this is what is 1 over phi lambda. Pretty simple. Okay. And now we construct the phi I lambda. Phi I lambda is simply this. Okay, so this is equal to minus lambda times lambda minus 2, right? Because in this product, you're just removing the first guy. I mean, when you multiply that, this will cancel. So what will be left over is that. And phi 1 lambda, and phi 2 lambda will be 1 times lambda minus 1 square. No? So lambda minus 1 square. Let me write it like lambda square minus 2 lambda plus 1. So phi 1a, what is phi 1a? So phi 1a is equal to minus a square plus 2a. Okay. So can we compute it explicitly? Well, I have to take minus of this and plus twice that, right? So this is minus 1 plus 2. So this is 1 here. And this is minus 4 plus 2. So minus 2. And this is 0 anyway. This is 0. And this is minus 1 plus 2. So plus 1. 0, 0, 0. And minus 4 plus 2. Plus 4 is 0. Because I have to take 2 times that. So it's 0. Okay, that's phi 1a. Now let's do the phi 2a. Phi 2a is simply, so yeah, if it this one. Sorry? Yeah, a square minus 2 lambda, 2a plus identity. So we have to take now again a square. This part I already did, right? I mean, this is the same as the minus of that. And then I have to add 1 to this. So minus of this plus 1, which is, so this cancels here. 0, 0, and here it becomes plus 1, and there is minus 2, plus 2. Did I do correctly this term? Is that correct? Minus 2. No, it's 0, isn't it? Ah, it's 0, yeah. Correct, it's 0. Yeah. So then this is 0. So it's very simple. The phi 1a and phi 2a are very simple. And now you can see what is it happening. I mean, so let's look at the S1 and S2 subspaces. So S1 and S2 subspaces, remember, is SI defined like that. Huh? Now take any vector. Any vector is for the form x, y, z. I mean, it's a three-dimensional vector, right? Now apply to that, say, phi 1a, right? What's going to happen? The third guy will become 0, right? So apply to this phi 1a. You will simply get x, y, 0, right? And if you take phi 2a applied to x, y, z, then you simply get 0, 0, z. So this is actually, in this case, this is two-dimensional and that's one-dimensional, right? Because x and y are arbitrary, right? So this is, you can have 1, 0, 0 or 0, 1, 0. So you can choose a basis. You can choose a basis for this 1, 0, 0 and 0, 1, 0. Choose a basis. Any vector can be written as x. This can be written as x times that plus y times that. And for this, you choose a basis 0, 0, 1. Okay. Now, okay. So now let's see if, what kind of. And I mean, indeed, you can check. Let's see. I mean, so what one of the things we proved was that this is the generalized eigenvector of consisting of the first with the eigenvalue lambda 1. Lambda 1 was 1, right? I mean, remember there were two eigenvalues, 1 and 2. Huh? So I mean, these guys must be generalized eigenvector with eigenvalue lambda 1, and okay, this must be lambda 2. So eigenvalue 2. So let's check that. So we want to apply. So I erased the a itself. Huh? What was a? Do you remember? I erased a. I should have kept it. So it was 1, 1, 0, 0, 1, 0, 0, 0, 2, right? This was a. So let's apply a on these vectors, x, and y. Actually, what I need is not just. I mean, so I want to prove that the subspace S1 satisfies the equation a minus lambda 1. So lambda 1 is 1 square should annihilate it, right? I mean, because this should be generalized eigenvector of that. So any vector of S1, this should give you 0. But well, a minus 1 square we already computed. A minus 1 square was this, right? Now apply this on any vector of this form, of this form, it is 0, because the only non-zero element is 1 here, but here this is 0, right? So this is indeed true, that statement. And similarly, for the second eigenvector, so you have a minus lambda 2 times identity. Lambda 2 is 2, so 2 times identity. But no, there's no power, so the power is 1, so it's just 1. Acting on S2 must be 0, right? A minus 2. A minus 2 is simply this guy goes out, right? I mean, a minus 2, let's see what is a minus 2. A minus 2 is, I have to subtract minus 2. So it becomes minus 1, 1, 0, 0, minus 1, 0, 0, 0, 0. And this acting on S2. S2 is of the vectors of this form. So only third entry is not 0. These two entries are 0, right? So it's clear that this, when you apply this on that, it's 0. So this fact, I mean, this is, so this subspace consists of generalized eigenvectors with eigenvalue 1, and this one with eigenvalue 2. This is only, it's only one dimensional, so obviously this is ordinary eigenvector, right? Which is in fact, it is already power 1. So this ordinary eigenvector. Now let's focus on this part, and you'll see that there is a rank 2 here. So let's focus on that. Did I erase? A minus 1 square. Yeah, so remember a minus 1 square, I erased unfortunately that. Here it was a minus 1 square. A minus 1 square, wasn't it this object 0, 0, 0, 0, 0, 0, 0, 0, 1, right? Okay, so a minus 1 square, that was what. Now let's look at, so let's look at a minus 1 itself. That will be the ordinary eigenvector, right? I mean, if there is a vector which satisfies a minus 1 acting on that vector equal to 0, that will be an ordinary eigenvector with eigenvalue 1. So a minus 1 is simply 0, 1, 0, 0, 0, 0, and 0, 0, 1. And we are applying it on this subspace, S1. So let's ask the question whether 0, 1, so this acting on this whole thing, I mean this acting on the xy 0 is equal to 0, 0, 0. That if you can find something like that, that would be ordinary eigenvector of rank 1. So you see that this equation, just multiply that, this gives you y, this gives you 0, and that gives you 0. That's equal to 0, 0, 0. So that means y must be 0. So the ordinary eigenvector is this 1, 0, 0. I mean, or x 0, 0. That doesn't matter. This is the ordinary eigenvector. But that's only one of them, right? What happens to the other guy? This guy is not an ordinary eigenvector, but it's a generalized eigenvector because in this entire S1 space, I have a minus 1 whole square is 0, right? So this conclusion is this is rank 1, and this is rank 2. This vector. Because this is annihilated by a minus 1 square. I mean, this is simply that. Right? But it's not annihilated by a minus 1, because a minus 1, when you apply that, this gives you y. It's not 0. It doesn't give you 0. Right? I mean, y is, for this one, y is 1. Right? So this is the rank 2. And in fact, this object, this vector, you can write it as a minus 1 acting on that. Right? So you see, so let's call this state as some vector v1. Then a minus lambda 1, which is 1 in our case, times identity acting on v1 is not 0 because it's rank 2, but it's going to be some, I mean, it's not a 0 vector, it's going to be some vector, right? It has to be that, because this is going to be linearly independent of compared to that, right? So it must have some component here. And you can explicitly see this is what we computed actually. This a minus 1 acting on 0, 1, 0 just gives you 1, 0, 0. I mean, so this in fact gives you 1, 0, 0, which is the other vector. Right? So this is just an example of, I mean, here it was very simple because I chose the numbers, chose the matrix conveniently, right? Otherwise it will be, yeah.
Okay, it is not clear to me how we concluded that is rank 1 and that is rank 2.
This was the first one was rank 1 because if you, so take x equal to 1, y equal to 0, and this is 0, right? Then this is true because when I apply here, you see when I apply in general, I find y 0, 0. But for y is 0 for this, right? I mean, just apply this on 1, 0, 0. Is identically 0, right? I mean, this is satisfied. So therefore, this is an ordinary eigenvector because I take it only 1 power, right? But on the other hand, if I had taken 0, 1, 0, this is not equal to 0, 0, 0 because this gives you 1, 0, 0. So in fact, this is 1, 0, 0. So this is not an ordinary eigenvector. However, if you take square of this matrix, a minus 1 square, a minus 1 square is that, right? Now apply that on this, it gives you 0, right? So therefore, this is rank 2 because a minus 1 square acting on that is 0, but a minus 1 acting on that is not 0, right? So rank 2. Yeah, so this, okay, I mean, yeah, this is the, I mean, this is just to show that all these statements are correct for this particular example, right? So today we'll go up to 1 o'clock, right? Yeah, okay. So if there are no other questions, then maybe I can move to the next chapter. Did you get the notes for the, I mean, yeah, okay, you got it, good. I mean, you can continue going through this chapter, first chapter, and if you have any questions, also next time you can ask me, right, in the beginning of the next lecture. Okay, so I erase now. So, so the second chapter is complex, I don't know, yeah, theory of complex functions. Theory of, what is the title? Anyway, I mean, the theory of analytic functions, yeah, theory of analytic functions. Okay, okay, first of all, before even doing this, I mean, I think you all know what a function is, right? I mean, let's take even one variable, or even, or it doesn't matter. Take some space, some space. Okay, let me just, for example, let me just put here example. Say two-dimensional space. Okay, this is my two-dimensional space. Huh? And what is a function? Function is something which just associates to every point here a number, right? Could be a real or a complex number, depending on whether this function is complex or real function. So for every point here, you give some rule which associates a number to that, right? I mean, maybe even two-dimensional. Forget. Let's look at the one-dimensional case. One-dimensional case. So one-dimensional case, you have just a real line, which let me use the coordinate x for the real line. Okay, and then I have some function f of x, which what it does for every point x here, it tells you, it gives you a rule. It's some number, and in fact you can plot it because I can plot it because it's only one-dimensional problem. I can plot it. It will be something, right, which says that at this point it has this value, function has this value. At this point the function has this value, and so on. Right? So that gives you. So it's a map from the space to real or complex numbers. It's a map. Now, of course, we already discussed a special case, which was the linear functions, right? But now I'm not going to just restrict to linear functions, arbitrary functions. Could be nonlinear, anything. It could be any function. So this is the idea. Okay. Let's see what else I need to say here. Okay, and so one of the notions is this you can actually generalize it. This you can generalize it to two dimensions, any number of dimensions. So if you have, say, in two-dimensional case, you'll have two-dimensional points will be labeled by two coordinates x and y, right? So this will be a function will associate a number for each pair x, y. It will be difficult to plot it now, but because it's so two-dimensional space, and if you have a real function, for example, that you can plot in the third-dimensional, right? And then it will be some surface up there. Right? So for every point, it will just, you go up there and to see what is the value. It will be some surface. So you can generalize it. Actually, you can, I mean, in this example I'm talking about, I'm thinking of real line or two-dimensional plane, x, y. But this actually, you can generalize it to even curved spaces. For example, the surface of a sphere, right? Surface of a sphere is a curved space. Right? Surface of a ball, no? It's a curved space. It's not a flat space, right? It's a curved space. So even there you can say that, okay, you can, I mean, example, so the underlying space need not be a vector space, although we will be restricting to only that for this chapter. Underlying space need not be a vector space. An example is a two-dimensional sphere, which we usually denote by S2. S2 means two-dimensional sphere. So it's what it is just take a ball and just look at the surface of that ball. Surface of the ball is two-dimensional, right? Because you have two directions you can move, or just staying on the surface. Okay. So in fact, for the that a surface of a ball can be you can give the coordinates azimuthal angle and the polar angle, right? Theta and phi. So if you draw the sphere here and say this is the north pole and that's the south pole, so draw a line like that, then any point here, and then look at the azimuthal angle will be this here. Huh? So if you take this is center and you draw a plane which is perpendicular to this axis, then that will be two-dimensional. So this is x and let's say that's y. It's difficult to draw now, right? It's perpendicular. Okay, this line is just going in. Okay, it is difficult. So any point here, if you project it down on this plane, it'll be some point here in this xy plane, right? So there will be some angle. Let's call it angle phi, which it makes with the x-axis, let us say, and then this angle, the angle which it makes with the say north this line, north to south pole line, whatever that angle is, theta. Okay, so any point on the two sphere can be labeled by just giving these two values, theta and phi. Theta ranges from 0 to pi. Theta equal to 0 is the line along the north pole. Theta equal to pi is the line along the south pole. Is the point at the south pole, at the north pole. And phi, of course, goes from 0 to 2 pi. And it's periodic because at 2 pi it comes back to original point. So this is the range, theta equal to 0. This is not a vector space. There's no sense of adding 2 points. This vector and that vector, you cannot, there's no sense here. Whereas in the flats, on the plane, there is a notion of adding. You take a point, which is a vector, another point, there is another vector. You can add that by usual vector addition. This again gives you another point in the space, right? There is no such thing here. It's not a vector space. It's a curved space. But nevertheless, also here, you can define functions. F of theta phi, which will be some equal to some real or complex number. Real or complex number. What it will do, for every point here, it will associate a number. Of course, it should satisfy the periodicity condition because phi equal to 0 and 2 pi are the same points. So it must be periodic in phi. So things like that. Okay, so you can extend it to. It doesn't have to be any vector space. It could be very complicated manifolds, the underlying space. But we will stick to this. For this chapter, we'll be actually working with this two-dimensional space. Actually, this space, flat space. Okay. Now of course, also a notion of the continuous functions. What is it? This is okay. This I just drew a plot here, right? But you could have also taken some discontinuous functions. For example, let's say if I plot f and x here, maybe it goes like that, and then suddenly it makes a jump here. This would be a discontinuous function. This would be discontinuous function. Here, what I have drawn here is a continuous function. Okay, this is, by looking at it, it's clear. This is discontinuous, that's continuous. But it will be nice to give some mathematical criteria, how you can talk about continuity and so on. So, what is really the notion of continuous? It means that if I take some point x, okay, it has some function has some value, right? If I go nearby, not far away, but just close by, take another point which is very near the original point, right? And if I look at the value of the function here, this value must not be very different from that value, right? And in fact, as I take the distance between these 2 points closer and closer, the 2 points closer and closer, this value should become closer and closer to that value, right? That is a notion of continuity. If that happens, then you say the function is continuous, right? Whereas here it is not the case. You see, you take the value here, it is this. You go a little bit higher, its value is up there. And this doesn't, as you take it, if you bring it closer and closer, nothing happens. This stays far away from there. Right? So this is discontinuous. So the way to say it is, so the way you say, you mathematically say is that what it means that for any epsilon greater than 0, but no matter how greater than 0, but it can be smaller and smaller and smaller. Okay? You look at the point x prime such that x prime minus x is so then what we are saying then there exists some delta such that delta again greater than 0, but again smaller and smaller, such that for f of x prime minus f of x modulus is less than epsilon for all x prime such that x prime minus x is less than delta. Okay? So to make it too clear, so what we are saying is that suppose you give me some epsilon, could be 1 millionth or 1 billionth, 10 to the minus 9 or whatever, it's as small as you wish but positive, something not exactly 0. But, then for so what I'm looking at, f of x prime minus f of x is less than epsilon, right? So let's take, let me draw it a bit bigger so that you can see more clearly. So let's say here is my function x f, and let's say a function is going like that somewhere, and I take some particular point here. Okay, this I call x. This point I call x. Then f of x is this value. This is f of x. Now what is f of? We are saying f of x prime. So let's see. This says that this value is different from that, but it's less than, the difference is less than epsilon, plus or minus epsilon, right? Because this is a modulus. So draw a band like this. So this is my original value. This is a f of x, and take this band. Draw a band. This is epsilon. Also, that is epsilon. Right. So then, what we are saying, this equation is saying that f of x prime must be somewhere inside this band, right? Because the difference between these two is less than epsilon. And see, any point here, if you take the difference between these 2 points, okay, is going to be less than epsilon, right? If this point is inside this band. Right? Okay. Now, x prime minus x we are saying is less than delta. So that will be this band here. You take a plus delta and minus delta from here. Then x prime will be anywhere in between. So okay. So what one is saying is that no matter how small you give epsilon, because when you make it smaller and smaller, you see this band is becoming thinner and thinner, right? We are saying that you can always find a delta such that for all points in between here, the value of f is inside this band, right? That's what it is. So as you bring it smaller and smaller, what we are saying is that you can still find a delta. So, I mean, this delta will of course become smaller and smaller, right? But you can still find some delta such that this is true. It won't happen if you have a discontinuous function. So let's say a function like that, it will not happen. Okay? I mean, say this is my x. Okay. Now I say I ask the question. So if I take epsilon, which is like this is the value of f here. I look at this here. Huh? This is if you choose epsilon to be less than this difference. Okay. You cannot find any delta which satisfies this condition. I mean, no matter how small you choose the delta, if you look here, the value of f here is not inside this band. Right? So this is a mathematical way of saying, defining this notion of continuity. So if this happens, then you say, then the function f is continuous at x. It's because it's a local statement. I mean, the place where you're looking at it may be continuous, but maybe somewhere far away, somewhere at a different point, it may be discontinuous, you see. So you can only, continuity is a question of local question. You can only answer this question at a particular point. Far away, I mean, at another point, it may not be continuous. Okay? So that's why you say, when this happens at some point x, then you say that function f is continuous at x. Okay. So this is one notion. Then there is a notion of differentiation. You know, you have done the calculus, right? The differentiation. So what you define the, what is a differential, how you take a differentiation is, so you define df by dx at some point x, at some point x, as f of x plus delta x, x plus, let's say epsilon, is that, let me use the same symbol as they are using. No, let's put a delta x, x plus delta x, minus f of x divided by delta x, and they take the limit delta x goes to 0. This may not exist, this limit may not exist always. But if it exists, then if it exists, meaning if it's something which is finite quantity, then you call that, you give it a name, you call it df by dx. This is the name. So again, the picture is, if you try to draw this picture, what we are saying, so x, and this is a function of x, and let's say I have some curve like this, which defines that I want to look at, say, the df by dx at this point, x. So what do? I take x, x plus delta x, this is x, this is x plus delta x, this point. You take the value of f of x plus, so value at this point, so that will be some value here. You take the difference between these two, this value and this value, okay, divide by delta x, and then start taking delta x going to 0 limit. So if that limit exists, then you say that that is a df by dx. Okay. It's clear that if the function is discontinuous at x, this limit may not exist, will not exist in general, right? Because, I mean, take the situation where the function is like this. Okay, here is x, and I want to compute the df by dx here. Now take x plus delta x. This is that. The value is here, right? The difference between this and this is some finite number. Okay. Even here, all the way, no matter how small you take delta x, this is somewhere here, and that this difference is finite. Okay, so numerator is finite, but denominator is going to 0. Okay, so something finite divided by 0 will become infinite, right? So this will not exist. I mean, so in this case, the limit does not exist. Okay, and you say that this function is not differentiable. Right? Here. Okay, sometimes, okay, you can also talk about. I mean, it may happen that this limit exists if you take delta x positive and take delta x to 0 limit. But it may not exist when you take delta x negative and then take the limit delta x goes to 0. Right? In fact, in this example that I have drawn here, when you take delta x negative, so meaning start from here and start approaching there, that limit exists. There is no problem with that limit. But this limit doesn't exist. Or it can also happen that both the limits exist, but they are different, right? Example is this. Take, let's say, like that. Okay, this is this function, and here I take x. Okay, if I ask the question, what is df by dx at this point? Well, if delta x is negative, I will approach from here. Okay, then it's clear it's a negative number, whatever that answer is, because f of x plus x minus delta x. I mean, I'm just taking delta x to be a negative number, right? Say minus 0.0001, whatever. Okay, but the value of f is positive, greater than the value here. So the numerator is positive, but denominator is negative because delta x is negative. I'm taking it. So it's going to be a negative quantity when I come from here. Whereas if I come from here, if I come from the right hand side and approach x, which means delta x is positive, so you see that this value is still greater than that, so numerator is still positive, but denominator is also positive, right? So the two limits in this case have different signs. I mean, it's not just the issue of sign. That just happened for this particular drawing. It may be the same sign. For example, let's say like this, and then like that. But the slope is not the same. I mean, I don't know how to draw. Let's say like this, and then like that. In this case, the sign is the same, but the value is not the same. Okay? See, when this limit exists, it's actually the slope of the curve. I mean, if you see, so let's try to see what's happening here. Come closer and closer here. No? Let's say, so here is my x and x plus delta x. Okay. So what are we doing? So you look at this triangle, right? You draw a triangle, right angle triangle like this. Then numerator is this length, right? And the denominator is that length. So it is if you draw the right angle triangle, is the tan trigonometric tangent of that angle, right? So this is, if you call this angle as theta, then what this is simply tan of theta. Okay. Now, if you start bringing it closer and closer, you see this angle theta will just become if you draw a tangent to that curve, whatever that angle makes with the x-axis, that will be the tan of that will be this value, right? So what actually this gives you is just a tangent to the curve at that point. It has information about the tangent to of that curve, right? Now, or the slope of that curve. That's what is called the slope. So at that point, what that angle makes what that tangent makes, the angle that tangent makes with the x-axis, right? And you take the tan of that. That's called the slope. So it gives you slope. So if at some point, when you come approaching it from the left, the slope is different from the one where you approach from the right, then it's the df by dx exists from the two limits, but they are different. You see. So there are all sorts of possibilities can happen. Okay. In the case where both the limits exist, okay, and are equal, you say the function is differentiable. Okay. That's the idea. I have still 20 minutes. Okay.
Dx is a limit of delta x as delta x goes to 0.
As delta x goes to 0.
That's right.
Sorry, what did you say again?
Dx.
Okay, this is just a symbol. This is a symbol. Yeah. I mean, you can think of that way. You can think of this as dx. df is a change in the f when the change in the x is dx. But okay, you're taking limit. Yeah. But this is a symbol. Just a symbol. Right. So now let's go to the okay. So now let's go to the something called the analytic function. This is the chapter, right? So we now consider. But let me just try to remind you about the complex numbers. Of course, you know, but complex numbers are of the form x plus iy, right? Where x and y are real numbers, and I is the imaginary number with I square equal to -1. This is and x and y are real numbers. X, y are real numbers. So if you can, this of course forms a vector space, because if you take two numbers, x1 plus iy1, this is one number, and another number is x2 plus iy2. You can define the addition. Just the real part you add separately, and the imaginary part you add separately, right? So this is the same as x1 plus x2 plus I times y1 plus y2. Okay. Of course, it's a form vector. You also have a notion of product. You can take the products, x plus iy, x1 plus iy1 times x2 plus iy2. just take the usual product, you will get, see, this times that is x1, x2, and this times that is I square, which is minus 1 times y1, y2, so minus y1, y2. This is real, both are real quantities, but then plus I times x1, y2 plus x2, y1. So, but this is again a complex number, and because this is real, that's real, and then you have I, so it's a complex number. So these are the standard. I think you all know these rules. Okay. Okay. So now what we want is, so let's define a complex coordinate. So I have this plane x, y, x and y, whose coordinates are x and y. I can define a complex number z, complex coordinate z, which is simply equal to x plus iy. Now, I want to consider a special class of functions. So, a general function on this two-dimensional space will be a function of x and y, right? Okay, there's no condition on this. Just okay. If you want continuous functions, okay, there will be condition of continuity. If you want differentiable functions, again, there will be condition. But I want to look at a special class of these functions. So, this is at the moment arbitrary functions. But we want to look at the special class of this function, class of the functions, which are differentiable in the complex sense, which are differentiable in the with respect to z. Okay. So what are we saying? We are saying that this limit should exist. F of x plus delta x, comma y plus delta y. Okay. So I have a point x y, and then so the picture is, here's my point x y, and there is another point nearby. So it will have some coordinate x plus delta x, comma y plus delta y, right? And then minus f of x y divided by. So let's look at what. Okay, so you know, but so complex number associated with that. So z is x plus iy. Now the complex number associated with that, let me call it z plus delta z. So what is so z plus delta z? Will be simply x plus delta x plus I times y plus delta y, right? That's the complex. So this is z plus, this I just call, this I just give it a name. I call it z plus delta z. Because after all, it is x plus iy is z, and the remaining quantity delta x plus I delta y is something small, since delta x and delta y are small, right? So I call that as delta z. So delta z therefore is simply delta x plus I delta y. So I divide this by delta z, which is, let me write explicitly here, delta x plus I delta y, and then take the limit, the 2 points approach. So delta x and delta y go to 0. If this limit exists, then you say that this function is differentiable. And you usually denote it by simply, if this exists, you call that as df by dz. This is just a symbol. Because you see, they are dividing by delta z, right? Delta z was that. Now, this is extremely restrictive. I mean, this is a very, very special class of functions. And you can, I just give you an example to show how this is so restrictive. Let's take a very simple function, f of xy equal to, say, x plus 2i y. A very simple function, differentiable. I mean, this is a completely continuous function in both x and y. It's differentiable with respect to x, with respect to y, right? Arbitrary number of times, right? It's all perfectly fine function, but it will not satisfy this condition. Okay. So let's do that. So we want to compute f of, so the numerator, f of x plus delta x, comma y plus delta y, minus f of xy, is simply, you see, is delta x plus 2I delta y. I mean, this is linear, so it's very simple. Okay. Now I want to divide this by delta x plus I delta y. So that's the same as that. Okay. But you see, okay, now I have to take the limit. Delta x and delta y go to 0. But we have to see, I mean, I can take the limit in different ways. Perhaps I can first take delta x goes to 0, then I take delta y goes to 0, right? Or perhaps I can take the other way around. First I take delta y goes to 0, then I take delta x goes to 0. Okay. So let's do the two ways. So I first do the first take delta x goes to 0, and then delta y goes to 0. Okay. So what will happen? First delta x goes to 0. I keep delta y finite and take delta x goes to 0. So this just disappears. So then what is left over is 2I delta y divided by I delta y. Delta y drops out, so you get 2. Okay, and then you take delta y goes to 0, you just get 2, right? So the answer is 2. Okay. Whereas if you do other way around, if you first take delta y to 0, keeping delta x finite, and then take delta x goes to 0. You see now, I keep delta x finite, but take delta y goes to 0 limit. Okay, this drops out, and you just get delta x divided by delta x, which is 1. So this answer is 1. So you see, the limits are they're different. So this doesn't exist. df by dx, df by dz for this function doesn't exist. It's not differentiable in the complex sense, in this sense. Partial derivatives exist. There's no problem with the partial derivatives. I mean, the df by dx, the partial derivative by definition at some point xy is simply f of x plus delta x, comma y, minus f of xy divided by delta x in the and limit delta x goes to 0. This perfectly exists. Similarly, partial derivative with respect to y exists, but this does not exist. df by dz has no meaning for this quantity, for this function.
So what do we conclude that it is not differentiable?
This function is not differentiable according to this definition. This is a very particular type of you see, I'm saying with respect to z actually, yeah, in some sense. It's not with respect to x or y, with respect to z. But delta z is that. And then of course, so in a pictorially you can understand what it means. You see, here I just considered two different limits. So here, what I'm saying is that here is xy, x plus delta y, x comma y, x plus delta x, comma y plus delta y. I can come in many different ways. I can approach this point from many different ways, right? I can come like that, right? Or I can come like that. You can come like that, right? There are from different directions I can come. So for example, what do I mean by saying first I take delta x goes to 0, which means this point is here, delta x is 0, right? Yeah. Sorry, delta x 0 is here, delta x is 0. This will be delta x is 0. So you are coming from up or from down, perpendicular, I mean vertical direction. Whereas if you first take delta y goes to 0, that means we are in the horizontal point. So we are coming in this direction or that direction. But in fact, there are infinite number of ways you can approach, right? In from any direction you can approach. And so this statement is a very, very strong condition that we are saying that no matter from which direction you come, the result of this guy must be the same. This ratio must be the same, right? That's a very strong condition. And indeed, we see that even for such a simple function, this condition is not satisfied. So functions I mean, those functions which are differentiable in this sense, they are called analytic functions. Okay? So if a function is differentiable at some point in this sense, then you say it is analytic at that point. Okay. That's the basic definition. I still have 10 minutes, so let me just state. So now you can immediately ask the question, what is the condition? I mean, okay, what does it mean? I mean, what can I look at the function and check and see whether this is true or not? I mean, in some simpler way. So there is something called a Cauchy-Riemann criterion. Let me erase this part here. There is something called a Cauchy-Riemann criterion. Cauchy-Riemann criterion. Okay. So the idea is the following. So it takes any function f of x, y. Let us split it in terms of real part and imaginary part. After all, this is going to be some complex number. At each point x and y, it's going to be some complex number. So it will have a real part and an imaginary part. So I write it like u of x, y. This is the real part of f, plus I times imaginary v of x, y. U and v are real functions, because I'm separating, by definition, because I'm separating into real part and imaginary part. These are going to be functions, of course, because this is a function. So the real part as well as the imaginary part will change as you change the point x and y in general, right? It will depend on x, y. So they are functions. Okay. So let's now try to write down this quantity. So let's f of x plus delta x, comma y plus delta y, minus f of x y divided by delta x plus I delta y. Well, this gives you, from this definition, simply u of x plus delta x. Let's separate this into real and imaginary part. U of x plus delta x, comma y plus delta y, minus u of x y. That's the real part, plus I times v of x plus delta x, comma y plus delta y, minus v of x y. This whole thing divided by delta x plus I delta y. Okay. So now let's do the same thing. Let's start taking two different limits. First I put delta x goes to 0, and then I take delta y goes to 0, and the other way around. So the two ways of approaching. One way you approach like that, and another way you approach like that. So if I set first I set delta x equal to 0 in this, and then I take delta y goes to 0. So when I set delta x equal to 0, this numerator simply becomes u of x comma y plus delta y minus u of x y, plus I times v of x comma y plus delta y minus v of x y divided by delta y, I delta y. And then I take the limit delta y goes to 0. So what am I going to get? So you could look at this separately, this thing. This divided by that in the limit delta y goes to 0 is just a partial derivative of u with respect to y. But there's an I there, so minus I. So this is minus I d partial derivative du by dy at the point xy. This is partial derivative. That's the definition of the partial derivative. And the second term, I cancels, and that simply gives you partial derivative of dv by dy at again xy. Okay. So this is the way when I first put, so I'm coming vertically down. Now let's do the first, let's put first delta y equal to 0. So that then you get, this is simply u of x plus delta x, comma y minus u of xy plus I times v of x plus delta x, comma y minus v of xy. And now I've set delta y equal to 0, denominator is simply delta x. And now you take the limit, delta x goes to 0. So you see that this is, first term is simply, I mean there's no I here. The first term is simply partial derivative of u with respect to x at xy. And then second term is I, partial derivative of v with respect to x, xy. Now, if this function f is differentiable in this sense, then these two must be the same, right? So we can just, I mean, this is real, and that's also real because u and v are real functions, so partial derivatives are also real, right? Similarly, this is real and that's real. So for the two complex numbers to be equal, the real parts must be equal and the imaginary parts must be equal, right? So equating the two, we get this Cauchy-Riemann conditions. So if you just equate these two, you find the real part. If you equate the real part, you get du by dx, partial derivative at xy, equal to here dv by dy at xy. And equating the imaginary part, so there's a real part, and equating the imaginary parts, you find dv by dx equal to minus du by dy. Okay. So you see, this is what is called the Cauchy-Riemann conditions. Okay. So any function for it to be analytic, right? Its real and imaginary parts must satisfy this equation, these partial differential equations. Okay, this is the Cauchy-Riemann condition. Indeed, you can check for the example I gave. You remember, the example was f was x plus 2i y. So u is simply x, and v is 2y. It will not satisfy. Du by dx is 1, dv by dy is 2, right? It doesn't satisfy. This one is satisfied though, because du by dy for this example, this is 0, and also that is 0. So this is satisfied, but not that. So for a function to be analytic, both these conditions must be satisfied. Okay. This is a very, very strong condition, actually. Okay. Now, I mean, actually, so you might wonder, well, to get these conditions, I just looked at two approaches, either coming from vertically up or horizontally, right? What about all these other directions? You know, I mean, how can I be sure that maybe if I consider some other direction, you might get even more conditions than this, right? But it turns out that this is sufficient. I will prove the sufficient next time, because now it's almost finished. But let me just give you an idea of what this condition means. I mean, I mean, formally, you see, these conditions I can write in the following way. If I write, suppose, so I think of z is equal to x plus iy, right? And let me introduce complex conjugate z bar equal to x minus iy. This is a complex conjugate, right? So, I mean, you have two variables here, and then this can be expressed in terms of, after all, if I can add this up. So x is equal to z plus z bar by 2, right? If you just add this to then you get z plus z bar equal to 2x. So x is that, and y is, you can see, is z minus z bar divided by 2i, right? So you can, it's like changing the variables. X, you can think of z and z bar as independent objects, but of course they are complex conjugates of each other, so it's not independent. And then x and y dependent on that. So actually, you can show that these equations is the same. Okay, so let's see. Let's try to write down d by dz bar. Okay, I mean, this I should put here in quote unquote, and just to understand this equation. So give you an intuitive understanding of what is the meaning of this equation. Okay, so let's just compute d by dz bar and using the chain rule of differentiation, right? Because you can write this as dx by dz bar, d by dx, right? Plus dy by dz bar, d by dy, right? Acting on any function of f of x, y. So this gives you, using the definition, dx by dz bar is 1/2, right? So what do I mean by partial z bar? Meaning that I keep z fixed and just change z bar, right? So 1/2 d by dx, and this one is a minus minus 1 over 2i. Is it minus 1 over? Yeah, minus 1 over 2i. So 1 over 2 I can take out. So this becomes plus I d by dy, right? Because it was minus 1 divided by I, but that's the same as plus I up. Because after all, minus 1 is I square. Okay. So now let's do the following. Let's look at this equation. So I want to get the combination dx plus I dy. So let's do the following. Let me write this on the other side. Okay, doesn't matter. Take this equation, and this equation you multiply by minus I and add them up. Okay. So multiply this equation by minus I and add it to that. So you get here d by dx of u and minus minus, so plus I times du by dy. So that is the same as d by dz bar of u. So this equation is d by dz bar of u, that way. And whereas other side you get, so this is equal to, we are saying, this is equal to dv by dy, let me write explicitly here, dv by dy. I mean, there is a half, okay. So let me add this up and multiply by 1/2, because there is a half. I mean, this is not important. That half is not important. Right? So you get 1/2, okay, dv by dy, and then I multiply by minus I d by dx acting on v. Right? That's what is this. Combining those two equations, you find this condition. Right? But this again, let me take out a minus I as a common factor from here. Okay, I take out this minus I. Okay, I mean, what is this? I can write this as, I mean, after all, I square is minus 1. So I just, this is simply 1, right? Minus I square is 1. So if I take out a minus I, you find that this becomes minus I by 2 d by dx plus I d by dy acting on v, right? But this is again d by dz bar, right? So this becomes minus I d by dz bar of v, right? So these two equations, by choosing this combination, is the same as d by dz bar acting on u is equal to minus I times d by dz bar acting on v. Take this on the other side. So this equation says that d by dz bar acting on u plus iv is 0, right? But u plus iv is the function f. So what we are saying that this is function f itself. So this means df by dz bar is 0. Right? So f only depends on z. That is what it is saying basically. Does not depend on z bar. That's the basic condition. This part, what I did, I just took the. I mean, let me write this equation other way around. Maybe the left hand side. Let me put the du by dx there. Du by dy. This is equal to minus dv by dx. Correct? I mean, I just rewrote that equation. Okay. Now what I do, I take this equation and add to that, I multiply this equation by I and add it up. So from, okay, let me repeat that again. So we are seeing, so left hand side, when I add this up, gives you d by dx plus I d by dy acting on u, right? This is equal to, on the right hand side, d by dy minus I d by dx acting on v, right? So I'm taking this equation, adding that, I times that. Okay. Now this is in fact twice. You see, this is what we call twice d by dz bar. So left hand side is simply 2 times d by dz bar acting on u, right? Now right hand side, if I take out a minus I is a common factor, then this becomes d by dx plus I d by dy on V. Why? Because you can, let's just open this, let's check if it is true. This times that is simply gives you this. This times that, see this is minus I times I is plus 1, right? It gives you that. So this can be rewritten this way, but this guy is simply 2 d by dz bar. So this is simply minus 2I d by dz bar acting on V. So Cauchy-Riemann condition is 2 times d by dz bar acting on U is minus 2I d by dz bar acting on V. So take it to the other side of the equation, right? So then you see that, so then you find that 2 is a common factor. So 2 d by dz bar U, and then I take it on the other side. So this sign will flip. So plus I d by dz bar V equal to 0. That is what this equation is. And then finally, you realize the fact that the U plus IV is F, right? So this is the same as statement dF by dz bar is 0. Okay. So what it means is the following. I mean, what we are saying is that if F is a function of x and y, but by those equations, I can write x as z plus z bar by 2, and y is z minus z bar divided by 2i, right? And what I mean by df by dz bar is that I keep z fixed and just changing the z bar formally. You see, that is a formal operation, because in reality it doesn't mean much, because after all z and z bar are a complex conjugate of each other. So there is no sense in which you can say that I keep z fixed, in z, but just as a formally. This is why I say that I put a quote unquote there in the d by dz bar. Okay. I mean, it's more correct to think in terms of this equation, but I'm saying intuitively you can basically say that, I mean, you can understand in a way that what we are saying is that this does not depend on z bar. Basically, that's what he's saying. If you write x and y as z plus z bar by 2, z minus z bar by 2i, then somehow z bar dependence must drop out. That's what we're saying. So in a sense, yeah. So function f is only a function of z. That's what he's saying, not of z bar. Okay. So what I will do is tomorrow, next time, I will start by showing that this is also sufficient condition. It's not obvious at all right now, because as you said, in deriving this equation, we just looked at only two directions, vertical and horizontal direction, right? But you have to look at all possible directions and make sure that no new conditions appear, that these are the only two conditions. Okay, so we'll discuss that and then move on to see. I mean, these functions will have very, very important applications. I mean, although this is a very subclass of functions, I mean, not a general function on a two-dimensional space, right? It's a function which only depend on z. It will have lots of important features. For example, for the real functions, you know that a function may be differentiable once, but there is no guarantee it will be differentiable second time, right? Or maybe it's differentiable second time, but no guarantee it will be differentiable third time, right? But for these functions, if a function is analytic, it's differentiable to any number of times around that point. I mean, so the very, very beautiful properties of this, and you can use this function, these techniques, to evaluate lots of integrals, for example, definite integrals, which we will see.